And yes, thanks. And this is when I would like to welcome Caroline Haglund-Stigner from RISE, who is organizing the HPT, and you will give us a presentation about the technology collaboration program.
Thank you, Benjamin. We'll start with Yes, I will give a brief presentation about the technology collaboration program on heat pumping technologies within the IEA. As I said before, my name is Caroline Haglund-Stigner, and I work for the Heat Pump Center, which is hosted by RISE. And the Heat Pump Center is the program office and communication center for the heat pumping technologies, TCP, abbreviation HPT TCP. So a couple of words about the HPT TCP. It's a technology collaboration program which has been going on already since 1978 within the IEA. It is an international framework of cooperation and networking for different actors working within the field of heat pumping technologies. It's a forum to exchange knowledge and experience, and it contributes to technology improvements by performing research, development, demonstration, and deployment projects, which we normally call annexes so far. Today, the HPT TCP has 20 member countries from America, Europe, and Asia. And in this context, heat pumping technologies include services such as heating and cooling, air conditioning, and refrigeration, and covers applications in residential and commercial buildings, in industries, in thermal grids, in cities and communities, and also in other applications. A couple of words about organization and management. The HPT TCP has an executive committee, which is the board, with 1 to 3 delegates from the different member countries. However, it's only 1 vote per member country. And this committee meets twice a year for meetings. Within all the most, at least, of the member countries, there are national teams, which are organizations representing national activities related to heat pumping technologies, which are national forums for discussion, networking, and creation of new ideas to be projects within the TCP. And representatives from those national teams meet at joint national experts meeting, normally organized once a year. And then we have the Heat Pump Center, which I work for, which is a central program office and communication center of HPT TCP. And finally, the annexes, the projects, which are international collaboration projects where new knowledge is elaborated. And this webinar here today is organized within one of those, namely Annex 58. Within the TCP, HPT TCP, we work a lot with those projects, research and development and so on, but also with communication and dialogues. So the Heat Pump Center, we publish the reports from the different projects, and there are already a couple of reports from this annex published on the website. Then we have the HPT magazine and newsletter, digital publications, which you can subscribe to. We run a website, and we're also active on social media, such as LinkedIn, X, and WeChat in China. Every third year, the program organizes a conference. The last one took place in Chicago last year, and the next one will take place in 2026 in Vienna, in Austria. We also organize these national experts meeting. We organize workshops and webinars like this one, and we also give support to different IEA publications with support them with data and review and so on. And we also work with other outreach activities. Finally, as I said, we publish a magazine 3 times a year, and here you can see the topics for the upcoming issues. The next one will be published in the beginning of May about flexibility and sector coupling. Then there is one in September on how to extend the working envelope of heat pumps, and the final one this year will be about retrofits, using heat pumps in retrofits, scaling up deployment with innovative solutions and overcoming barriers. If you are, we will share the link to subscription in the chat. You can also find the magazine on the website, and if you want to contribute with articles to the magazine, please contact us. And finally, some contact information here to us, the chair of the executive committee, and also us working for the Heat Pump Center. And you can see my colleague Medical is the one who is technical supporter in organizing this webinar today. Thanks for me.
Yes, Caroline, thank you very much for this nice presentation. I think it gives a very good overview of the activities in the TCP, and I can also personally only recommend to use the information materials. I think it's very compact, very good information you're getting both in the newsletters, but also in the magazine here. So make sure to follow these materials here. I will go back to the presentation here. So yes, I will give a brief background for Annex 58 and how it actually started. This Annex projects, Caroline has explained it. They are often focused on gathering and communicating information materials about a certain defined topic. And this might be kind of a weird project, because projects typically about project development or technology development, but these are more focused on gathering information and actually communicating them. And why is that possible? And I think this is why is that important? And this becomes very clear when looking at Annex 58, and if we look back at how it actually started, because we had the Annex from 2021 and 2023. And when we started, there has also been a previous project on it earlier, which was called Annex 48. And this Annex 48 was also on industrial heat pumps as general. And during this Annex 48, there was a lot focus on actually gathering the state-of-the-art information about industrial heat pumps. And in this Annex, the focus was very much on actually realized installations. And the figure I'm showing here was one of the main results from Annex 48 at that time. So you can see many of heat pumps. There was a huge database of industrial heat pumps to show that this technology is actually working, it's in operation, it's saving CO2 emissions, it's increasing energy efficiency and so on. But most of these technologies, actually the very vast majority of all this installation was below 100 degrees. But we, working with industrial heat pumps, knew, of course, that it is also possible to go to higher temperatures and apply the same principles, the same technologies to even higher temperatures where it makes sense. We also knew this figure here, you have seen it earlier, it's from a white paper which we have written to make aware that heat pumps could be used at even higher temperatures, especially targeting the temperature range between 100 to 200 degrees, maybe even higher temperatures. And we know that heat pumps are actually very promising for these kind of temperatures and are the preferred solution for really a range of applications. We also indicated some different sectors here, like food and beverage sectors, pulp and paper, chemical industries, but also machinery and non-metallic minerals. And just to get an idea of it, like 2/3 of the entire total energy demand in industries is used for process heating, and approximately 1/3, a bit more than 1/3 of it, this is like process heat, could be decarbonized by electricity-driven heat pumps. And this shows the huge potential, but at the same time, we could actually also see that this is not very much understood in industries. We can also see that these studies here were confirmed by other institutes like the IEA later on in May 2021, they actually published this net zero by 2050 roadmap. And you have also seen these figures before. I can also share it here. It's a very popular figure where you actually can see that then up here, it's a low and medium temperature heat demand by technologies, and it's up to 400 degrees. And if you see here, what's happening between 2020, that's the first row, to the second row, 2030, and the low and medium temperature heat demand, you can see that the light purple one is being phased out. That's fossil fuel heaters. And you have here the heat pumps kicking in. That's the orange ones. So it's the main share to be expected, as a main change to be expected, that heat pumps are replacing fossil fuel heaters by 2030. And with that in mind, and considering this public understanding that heat pumps could maybe provide heat at 90 degrees, there have a lot of ammonia systems, for example, maybe up to 100 degrees, but not more than this. We saw a huge gap for creating some communication materials. We know that to exploit these potentials, you need different developments. You need, of course, technology developments. You need the end users to understand it. Boundary conditions will become more favorable for industrial heat pumps. And all this will lead that this technology awareness, which we created here, will result in a market deployment later on. But this understanding, these information materials, this is very important, because technology providers, they need a business case to develop their technologies. They need to know that there's a market where they can use their technologies. Otherwise, they would never develop a heat pump if there wouldn't be a market. And end users, which can create this market by committing to heat pumps, they will obviously only commit to heat pumps when they know that these heat pumps will be developed. So this is a chicken egg problem. And in the middle, we see communication is key to overcome it. And this is how we then facilitated Annex 58 at that time. And we said, okay, what is important? How can we communicate this message here? We said we should make sure that we create a clear technology overview. So that was our task one, to gather information about available technologies, but not only available technologies, also those technologies which are on their way, under development, and which will enter the market during the next few years. So that was task one, very important to give this technology overview. Then it was very important on how you could actually integrate heat pumps. We made integration concepts for a number of different processes. So here you can get inspiration of the different scenarios on how to actually integrate heat pumps in your processes. Task 3 was about the application and transition. So we have these nice concepts, like this is our overall target, and that's the question, okay, how can we actually implement it in a real case? So how can we master this transition and realize these blueprint concepts as developed in task 2? And then we noticed as a last point, one of the barriers was also that we noticed that the specification and testing of heat pump specifications is a barrier. And we also developed some recommendations and suggestions here on how this could actually be improved. And with that mission, we facilitated Annex 58 to gather this information and to disseminate them widely. The Annex 58 has grown a lot. In the very end, we got like 14 countries, and for each of these countries, there's several organizations joining and being represented. So we had the pleasure to coordinate it, but there are really many organizations who contributed to this development. And you can see it by like 14 countries, includes everybody from, or a lot from Europe, but also from Asia, Japan, China, South Korea, and on the other hand, we also had US and Canada here. So it was a huge task to coordinate this also. It was a 3-year project, and one of the last notes here is like all the information being shown here today is available on the homepage down here, heatpumpingtechnologies.org, Annex 58. Just Google for Annex 58, high temperature heat pumps, you will find all the information you need here. And this is how we then started Annex 58. And this is what I had from an introduction here. And from here, I will hand over to my colleague Jonas and Cordin to give a presentation of the task of the state-of-the-art review of high temperature heat pumps. So yes, Jonas, please share your presentation.
Great. Thanks, Benjamin. I trust you can all see my screen now. It's a pleasure for me to present task 1 here in the Annex 55 together with Cordin the focus here is on state-of-the-art for high-temperature heat pumps and realized demonstration cases. Yeah, so obviously, this is the first thing we did in the annex. As Benjamin explained, we wanted to create a big and thorough overview about the state-of-the-art for high-temperature heat pumps. And the way we approached this was to try and standardize the information we could see of various suppliers and contact them and use this big network we have in the Annex group. And actually, we ended up creating 37 different two-page descriptions, each of them describing a high-temperature heat pump technology. And you can see an example here from the Spanish company Rank, how one of these descriptions look like. We have some tables with the performance, the COP at some different temperatures. We have a fact box showing the key information, and you can also see it here on the left-hand side. What kind of working fluid is this technology using? What is the compressor type? What is the cost? Some suppliers also stated that, and how big is the system? And actually, we were a bit surprised how many suppliers ended up giving insights, and that there were so many technologies already on the market. But I actually know that there are even more suppliers out there. So if anybody's on the call here, then please contact us afterwards, because we would like to maintain this overview and add more suppliers. But the suppliers who answered our inquiry can be seen here, the company logos, and it's really a wide range of different companies. There are some big, well-known energy companies. There are some compressor manufacturers originating from the commercial refrigeration industries, and there are some startups. And also, it's very much there's a big geographical spread in the suppliers. And here I just switch so you can see there's a picture from each of the descriptions corresponding to the logo we had before. And as you can see, it's really different what kind of technologies we're seeing. We have some really big industrial systems, such as the heat transformer seen here, big piston compressors. Some of the systems are still 3D drawings, being a little bit further away from the market. Some of them are also smaller system. So really a wide range of different technologies. And of course, all this information we received, we tried to structure that in quite many ways. Here we can see just a simple table with some of the very key information. Here it's listed all the suppliers after the minimum capacity of the system. And I just shown here the various compressor types, working fluid, maximum supply temperature they can deliver, and then a quite important factor, this TRL indication, which means the technical readiness level, where 9 is very high and very mature, and a lower number is correspondingly more immature. And one of the things you might notice if you know a little bit, have some insights to heat pumps, is that there are many different working fluids, but actually quite many of them also are using natural refrigerants, such as hydrocarbons and water. And then the next slide here, so that's basically just a continuation of this list here. And you can see if we look again at the capacities, it's going more and more up. And actually we have some suppliers who stating that they can deliver all the way up to around 100 megawatts. But let's take a little deeper look into some of the, if we have look at it and use some metadata on it. What I have plotted here is each of the suppliers has a corresponding dot and color in this figure here. And then I have plotted the capacity on the x-axis, and please note that this is logarithmic, and then the maximum supply temperature this heat pump system can deliver. And I think one of the trends we could see is that actually, if you want the heat pumps at the very high maximum supply temperatures, then it also corresponds to the ones having a higher capacity. So you can see there is somewhat of a maybe not linear, but at least there is a trend that we have the higher maximum supply temperatures also at the higher capacities. And this is really, again, quite different technologies we see here. Some of the very high temperatures here is systems that is compressing steam. And then some of the relatively high temperatures, for instance, this Enerin and Olvonder, these are Stirling heat pumps. And you can see that if you look at the corresponding dot here, that's listed, corresponding to the highest temperatures. But yeah, basically a lot of system around 120 degrees and 160 degrees. We also plotted for the suppliers who stated the specific investment cost, we plotted that against the mean temperature lift. And you can see that on the left-hand side here. So the mean temperature lift, that is basically the difference in temperature we have between the heat source and the heat sink. And you can see that it has a cost in general if you want to have systems that can obtain a higher temperature lift. Then there is also some tendencies that the cost going a bit up. But of course, there's a lot of unknowns in this, exactly what the price are. But I think it's fair to say there are some general trend here. And then we also asked the suppliers about the expected lifetime. And I think it was quite clear to see that for the systems that were relatively big, they also stated a longer lifetime. So maybe this is more industrial compressors, where the smaller one is maybe coming more from a commercial refrigeration business. But still all of them quite high lifetimes. Then we looked a bit more on the performance. What we have plotted here, if we start looking at the figure on the left-hand side, is the Lorentz efficiency in relation to the mean temperature lift again. And the Lorentz efficiency, that's basically a parameter you can use to describe how efficient your heat pump system is. It's looking at the theoretical maximum COP you can gain in your given boundary conditions. And we can see that it was quite a big spread of the Lorentz efficiencies, but if you're going higher up in mean temperature lift, we also have a corresponding higher Lorentz efficiency. But again, it depends really on the application type. So we have these systems also compressing steam. That's the black dots here. And if we look at the figure on the right-hand side, we have plotted all the COP that was stated against the mean temperature lift. And that's maybe an important general aspect to state, at least for people where heat pumps are a bit more new, is that there is just, even though we have a very efficient heat pump, which is the case when we have a Lorentz efficiency around 60%, and there is just a limit how high a COP we can expect. And we can see this curve here when we are approaching the temperature lifts above 100 degrees Celsius. It's not possible to have a COP higher than 2. And then we try to do, after collecting all of this information, and please go into the homepage to dig more into the various descriptions. We try to do some general perspectives, which is of course also always a bit difficult, but I think we could safely conclude that there are clearly a picture that we need to first of all look at the capacity and the sizes of the systems. If we have system above 10 megawatts, we are looking at system coming from the process gas industry, where there has been compressors running for decades already. And then if we are looking at this, I would say smaller system, you can still argue that it's relatively big, but between maybe 200 kilowatts to 10 megawatts, we are in the upper part of this figure here. Here we have already seen commercial application of heat pump systems that can go up to 120 degrees, and we'll just in a few minutes see some more examples of that. If we are then looking at a bit higher temperature range, ranging from 120 to 160, there is a lot of demonstrators ongoing right now. There is a lot of R&D projects investigating that. And then if we go a bit higher up, so above 160, we can see that it's things that are starting to come now. We are here a bit, there's a little bit longer time range than that. So maybe some of the first demonstrators available here would start coming next year. And then if we go down to the system above 10 megawatts, there is already demonstrators available at the temperatures up to 120 degrees. But here, I think the important aspects to mention is that we already have some compressor technology that's well proven, but of course there needs to be some kind of technology transfer for integrating heat pumps at the various end users. But up to 120, the demonstrators are available, and for the big system above that, we are kind of on the same page as the system, smaller system above 160. So that was a few words on the technology review that we did. Now I will stop our presentation and hand the word over to Corin, who will go more into describing the realized demonstration cases.
Thank you, Jonas. I hope you can hear me. Can you give me a sign?
We can hear you.
Can you hear me?
Yeah.
Okay, great. So in the following, I will show you realized demonstration cases. We have received 2-page descriptions from various companies, and these fact sheets contain important information such as the application, performance data, operating hours, compressor technology, some cost info, energy savings information, and importantly, the CO2 emissions savings and other factors, and also a contact information. So the first slide shows an overview of the collected demonstration cases. This table can also be found in the Task 1 report and also on the Annex 58 website. The table is structured into different topics like supplier, industry, process, heat source, heat sink information, heat pump type, the refrigerant, and also compressor type, the COP data, and operating hours. And here the color is a little bit, the table is a little bit color coded. So we have it's structured a little bit by application, process, and industry. So for example, here, these are examples for steam generating heat pumps, including MVR technology. Then here we have thermal separation processes, which includes distillation processes. And then we have several cases about drying. Drying is a very important process, and heat pumps have here quite some applications. What we can see is that conventional heat pump cycles, closed cycles, reached here temperatures up to 138 degrees using HFO refrigerants in this case. But MVR goes higher to 211 degrees saturation temperature with piston compressors and multiple cylinders. Then we have the Stirling heat pumps that also reached higher temperatures up to here 183 degrees. So this graph shows a box plot of the target sink temperatures, which were here summarized. They are between 115 to 240 degrees. And this graph shows the COP, the heating COP as a function of the mean temperature lift. So the mean temperature lift, like Jonas mentioned, is the mean temperature, so the logarithmic mean temperature between the inlet and outlet temperatures on the heat source and heat sink side. And it varies from about 26 Kelvin to 145 Kelvin here in these cases. And as expected for the closed cycle compression heat pumps, the COP decreases with higher lift, but they are quite at a relatively quite high level. Now we can overlap the MVR cases, and they achieve higher efficiency than the closed cycle heat pumps because they work in open mode of operation and have a higher efficiency. Then number 4, for example, here is a Stirling heat pump, which achieves the highest temperature lift, followed by the MVR applications. So in the lower temperature lifts, there are more the closed cycle heat pumps predominant technology. And for steam generation, we have different combinations. We'll see this later. Here, this graph shows the Lorentz efficiency, which is the maximum, let's say, theoretical maximum efficiency versus the temperature lift again. Here first for the closed cycle heat pumps. So we have here ranges of, let's say, 40, 50%. And then when we include the MVR systems, we have achieved Lorentz efficiencies up to 70 to 80%. Now, the first demonstration case here is from the Horizon 2020 project dry efficiency, especially in drying processes. So the installations are from 2019 and 2020. The refrigerant used is a HFO, the R1336MZZZ. On the left is the example of the brick production at Wienerberger in Austria. And the heat pump consists of a twin cycle with 8 piston compressors. On the right, we have the heat pump from Agrana, starch production, also in Austria. And the heat pump provides here hot air up to 160 degrees for the last zone of the starch dryer. So there are substantial energy and CO2 savings possible. These two examples show it quite nicely. Also, cost savings are stated here, 60,000 euros per year and 43,000 per year, so that the payback times can be, let's say, cost effective. The COPs fit with other experimental data from other industrial heat pumps. So what are the learnings here? They learned about material compatibility, so the lubricant, refrigerant, and sealing materials. They also learned about the mechanical design, about vibrations, about integration into existing infrastructure, and also process control was one of the learnings for startup procedures or data control measurement devices. The next demonstration case is from the electronic industry. So this includes processes for drying or heating coils for electric transformers. So this works with a dry furnace where the copper wires are coated with paper using special resin melts. And the application requires here 130 degrees hot water. So conventionally, they would use a boiler, a gas-fired boiler to provide the process heat. But here they have heat pumps and they have been integrated 2012, so more than 10 years ago. And the heat source is waste heat from the annealing furnace. And this is upgraded also using thermal storage to this 130 degrees. The COP is around 3. And compared to the steam boiler, CO2 emissions and energy costs could be reduced by 60 and 65%. So the special learnings here is that detailed analysis, energy analysis of the heat demands and of the waste heats before the installation of the heat pump was key for the success. The next demonstration case shows steam generation via MVR technology from Spilling, which has piston compressors with multiple cylinders. So low pressure steam is upgraded or recompressed to high pressure steam. The left example shows a 6-cylinder steam compressor at a paper mill in Sweden. And the right example shows a steam compressor for recycling excess steam in a chemical plant in the UK. And it shows a double stage steam compression with a 6-cylinder steam compressor. So here the steam is compressed from 5 bar absolute to 19.5 bar. And the capacity was 11 megawatt. So the COP, which was 5.3, is based on the condensing heat and also the heat from the condensate tube cooling to 105 degree. So special learnings here is that optimizations of the discharge pressures. So if this could be reduced, to lower pressures, then okay, it's clear electrical power can be reduced, the demand of electrical power, and so the COP and efficiency of the system. The investments are here in both cases around 2.2, 2.5 million euros without the integration. The capacities, as I said, 11 and 12 megawatt. So for steam generation, there are various heat pump concepts. We will see it later on as well. But the first one we need to consider is MVR, so mechanical vapor recompression. Then we have, as a second, a combination with MVR and a flash tank, where water is the refrigerant or the working fluid. The third is a closed cycle compression heat pump with a flash tank and MVR. And the fourth concept is a closed cycle heat pump with a direct heat exchanger to generate the steam. So in the following, we have some examples for all these cases. So this case is also a demonstration site developed in the dry efficiency project. It's at Scanship in Drammen in Norway for biosludge drying. And this demonstrator is an open loop MVR system and uses a two-stage turbo compressor with speeds up to 90,000 RPM. So steam from the dryer is recompressed from 1 bar to 4.2 bar, and this gives a pressure ratio of up to 2.1 per stage. The demonstrator achieves a capacity of 500 kilowatt, and as an acceptance test, 50 tons of garden waste was dried in this demo. The next demonstration case shows steam generation via MVR and a flash tank. The left example shows a sewage sludge drying at Hadano Water Treatment Center in Japan. The compressor technology is a twin screw compressor and a roots blower. Starting from 93 degrees and then upgrading it to higher pressure. The example on the right is steam generation via MVR blower technology from Pillar in a EPDM plant. So 8 units are installed here, and these are turbo blowers starting from 60 degrees and generating steam at up to 131 degree. So this is a 10 megawatt capacity installation, and the investment costs were about 6.8 million euro, but the cost savings were or are 4 million per year. So this means a very cost-effective solution and payback time of, let's say, 1.7 years. This demonstration case is a steam generating heat pump with closed cycle and flash tank combination. It is an application for distillation of bioethanol at Hokkaido in Japan. So these are 5 units of the Kobelco SGH 120 heat pumps, and they installed in 2012, 2013, so already over 10 years in operation. And so the heat pumps are arranged in parallel so that they can increase the capacity. The heat source is the distillate cooler at 60 degrees, and the heat sink is steam at 110 degrees. And the heat pump covers around 70% of the steam demand. And as a backup boiler, there is still a backup boiler, and this would cover maybe 30% of the heat demand. So the customer is very satisfied with this solution. It's a very reliable solution with the heat pumps. Then this case is a case with the high lift heat pumps from Olvondo for steam production at AstraZeneca R&D Center in Gothenburg in Sweden. These are actually, there are 3 of these high lift heat pumps, and they are based on the Stirling engine with helium as a working fluid, and they have piston technology. One of that unit has a capacity of around 500 to 750 kilowatts, They have 3 of them, so over 2 megawatt capacity. The supply temperature is very high, 183 degrees, and at a temperature lift of 147 Kelvin, a COP of still 1.7 is achieved. The investment about 1.8 million euros for this over 2 megawatt installation. And a special learning is that this concept of Stirling heat pump has been proven here and demonstrated, and the steam at high temperature 180 degrees range has been delivered. Then this demonstration case is about Scale Up Cascade high temperature heat pump, which is here for simultaneous process heating and cooling. It has been developed by Sintef in Trondheim in Norway, and it has been demonstrated at the dairy of Tine in Norway. So it's a cascade heat pump using propane in the lower stage and butane in the upper stage as refrigerants. The heat pump can run in a ice water production mode or in a dry cooler mode. So in the ice water production mode, a COP of 3.4 is reached. And here the COP is the combined COP of heating and cooling. So the specific investment cost for this 300 kilowatt heat pump unit is between 500 to 700 euros per kilowatt. Last but not least, a very recent installation of a high temperature heat pump, or several ones, at Ahasgra distillery in Ireland. So it's the first zero emission distillery in Ireland. And there are 3 high temperature heat pumps from Oilon installed to produce a combined process heating and cooling. So 115 degrees for distillation and 85 degrees for hot water using the subcoolers of the heat pumps, and also cold water or cooling water of around 35 degrees is produced. So this picture here on the right shows the storage vessels, which were also installed, and then the high temperature heat pump on a crane before installing it in the distillery. So the project costs, the turnkey costs were about 1 million euros, but a lot of cost savings were achieved. So the payback was a little smaller than 3 years for the whole project. So as a summary, Jonas and me, we showed you different heat pump technologies. So the high temperature heat pump technologies are continuously developing, and they increase the potential for further demonstration applications. We have seen different TRL level, costs info, capacity info, temperature info, and various technologies from different suppliers. The demonstration cases have also been reviewed here shortly. So the applications we have seen are in drying applications, hot water production, steam generation, and thermal separation like distillation. So about 15 cases have now been collected and really described in fact sheets, and this is all available in this report and also on the website, where we can see there are some there is some diversity in the different examples, but some common aspects have been found, like the TRL levels, the supply temperature, and specific investment costs. So the task 1 report is available. So on the website, as mentioned, it's 173 pages long, and 33 contributors helped to make this report. 13 countries participated. So here, final slide is the table of all researchers that contributed to this report.
Perfect.
So thank you for your attention. And Jonas, maybe you have some last word, or otherwise we give back to Benjamin.
Yeah, thank you very much. I think we have some, I think it was a very good presentation and very relevant, and we are a bit over time, but I didn't dare to interrupt you because I think it's relevant to also have the demonstration cases. It's very important to also show these. But let's take a few of the questions, and all of you have hopefully seen. You can put your questions in the Q&A. There are some questions I can briefly answer. So yes, presentations will be uploaded in the course of the next 1 or 2 days. The webinar is being recorded. This will also be made available during the next 1 or 2 days. There has been asked for some specific suppliers like Atlas Copco, but also others, if they aren't also producing heat pumps. And here the answer is also yes, they are, but we can also only show the information which are provided. So make sure to send them an email and ask them to send the information to the annex. And now I have 1 to 2 questions for you, Jonas and Cordin. Regarding geography, are there any regions or countries which you think were very particular, let's say, moving forward? Where do we have most technologies available compared to, for example, Japan, China, Europe, or US? Do we see any trends?
I think, yeah, in general, we could see that quite many descriptions were available from Japan, and they were quite advanced. And as Cordin just showed, systems were already operating for over 10 years ago. They were, however, a bit smaller systems, so below 1 megawatt, and they are not being sold in Europe. So that's at least one trend. And then I think we could see, for instance, there was a lot of systems from Norway. I think, yeah, 6 or 8 different suppliers from Norway. So that's also very, very relevant to know. But in general, I think the biggest impression was that we just got so many suppliers, more and more was coming. And then there was a bit of a, I don't know, funny trend. Okay, we have 37 technology suppliers, but actually we only had 15 demonstration cases. That also somehow shows that, okay, more and more technologies are coming with suppliers, but we need to get more demonstrations and more examples in real life. Maybe we have something to add, Cordin.
Yes, I would confirm my view as well with Jonas' view. Europe is for sure a leading, let's say, in this field, but there are also many applications in China and in Japan. So I would say Japan is a pioneering country in this high temperature heat pump technology. So I think many countries follow up, and as it is a technology which is, let's say, supplying hot water or steam, this is quite versatile, so the applications can be very broad.
Yes, thank you very much. And one last question, which you can maybe answer briefly. We have published this report, I think, in August last year. We have published a lot of these technology descriptions and also demonstration cases. What was the feedback from industry? So who was using these information, and what was the feedback on this kind of information you have gotten?
Yeah, first of all, I would say that the interest has been enormous. We've gotten so many inquiries about where can I find this description. I want to have my description included as well. But yeah, I got a feeling that actually quite many end users are looking at this, and consultants doing review of the technology, helping their clients looking for new ways to decarbonizing their process heating. Yeah.
Yes.
I also think, I mean, the table which summarizes all the technical info was quite useful as a selection guide. The cost questions, in my experience, was always high level or highly questioned. So what is the cost of this heat pump, and who can deliver certain capacity? That was mostly requested.
Perfect. Thank you very much. It was a very good presentation. Thank you also for answering these questions. We have to move on to the next task. And while moving on, I think there are 21 questions in the Q&A you could spend some time on answering. So we will move on to task 2, where we look at integration concepts for heat pump-based process heating. And this will be my colleague Virginia giving presentation together with Roland Schlosser from University of Paderborn. And I hope we can maybe catch up a bit on time to be not too late in the very end. So please, Virginia.
Yes. So
you start
yes.
sharing. Yeah.
Yes.
So,
So we agree that I will be sharing a presentation, and Florian is going to start. Then we're gonna alternate. Okay.
great. Yeah. Hello and welcome also from my side. Virginia and my person, Florian Schlosser, we are happy to report on our joint activities in task 2 of Annex 58 about integration concepts of high temperature heat pumps. In addition to Gordon and Benjamin, we would like also to thank all other colleagues who have contributed to with their integration concepts to this task. First of all, I will explain the terms and templates we have used to derive uniform integration concepts. And each of these integration concepts contains information on the process and systems. Then we will give information about the suitable integration points and the used or the suitable heat pump concepts. Then Virginia will demonstrate this logic using 3 examples from the different heat pump application. One for heating along large temperature glides, the other one for steam production, and then one example from hot water or thermal oil production. And finally, I will talk about some key learnings for the development of integration concepts. Yes, as we have already heard before, the idea behind task 2 is to make people aware of sensible application possibilities. And therefore, we wanted to develop kind of blueprint integration concepts of different heat pump concepts for representative, widespread, high temperature reference processes, like, for example, spray drying, sterilization, other steam consuming processes, or hot water and thermal oil production processes. Apart from that, we have agreed on a systematic to describe and categorize integration concepts according to the process description, the integration concept, the heat pump application, and the heat pump concepts. And what does this mean? You can see on this slide. The concept development always starts with the requirements of the processes in terms of supply and target temperatures, heating and cooling demands, as well as the energy medium production pattern like continuous or batch operation. This you can see on the upper left area of the slide. And if we then follow the arrow, the next step is different integration points can be considered for each process. So which here are marked by the black boxes in the process layout. And every black box stands then for one or more heat pump concepts. And each heat pump concept can be clustered according to different applications. And in this context, we distinguish between the applications heating along large temperature glides, steam generation, hot water, or thermal oil production. And then for each heat pump application, of course, there can be multiple suitable heat pump concepts available. Various heat pump concepts can then be provided by different manufacturers, which was part of task 1 and on which Jonas and Gordon has just reported some minutes ago, and therefore I won't go into much more detail here. Then
yes.
Next slide, we have used for this purpose 2 templates for the standardized collection of relevant process and energy data, and in order to have a uniform graphical representation. And one of these templates is for the integration concepts and contains description on the processes and potential integration points. And the other one is for heat pump applications. And in this heat pump application, different heat pump concepts were described, which are suitable for fulfilling the specific requirements in the applications areas. Yeah, at this point, I will go. Virginia will take over and present the systematic using 3 examples from the 3 heat pump applications.
Yes. So I'm gonna give 3 examples about how we have collected the information and described the concepts according to the criteria that Florian just explained. The first example is spray drying. So drying is a very energy-intensive process, and convection drying basically consists in putting the product to dry in contact with the hot drying air, and this so the supply air, the fresh air, is conditioned to the temperature required by the dryer, and then leaves the dryer with the high humidity, and it's then cooled and dehumidified. And traditionally, without heat pump integration, then the conditioning of the supply air is done by boilers driven by fossil fuels most of the times. On the right, while on the right side of the slide, you can see the temperature process requirements in a specific case of milk spray drying. So you can see the temperature requirements for the supply and exhaust air. So you've seen the process, how it is without a heat pump integration. While integrating a heat pump, the humid exhaust air is used as a heat source for the heat pump, and that then is going to upgrade this heat and take the supply air to the temperature required by the dryer. So there are several integration concepts possible. So here we are show the simple concept in which the humid exhaust air is used directly as heat source, while in the second concept there is an intermediate cooling circuit. The advantage of using an intermediate circuit is that it is less efficient, but it has advantages in case of contamination of the exhaust air, and also because in case of leak, we don't risk to have the refrigerant going into the airflow. Then for this integration concept, there are different heat pump concepts, pump designs that are possible. In general, for drying applications, since air has low heating capacity and density, then there is going to be large temperature glides on the sink sides. So the heat pump concepts that are more suitable for this application is concepts with large temperature glides, such as Brighton cycles or transcritical cascade cycles. The second example is an example of steam generation for distillation. So distillation is a separation technique that is widely used and very energy consuming, and basically requires steam to vaporize the most volatile substance. So in this case, for example, ethanol in a water solution. And then it requires also a condenser to liquefy the distillate after the distillation. In a traditional system, then the steam for the distillation is going to be provided by fossil fuel fired boilers, while the cooling for the condenser is going to be supplied by a cooling tower or river or a chiller. While integrating a heat pump, so the heat pump is going to provide the steam, and the heat source for the heat pump is going to be the cooling from the distillate condenser. So the steam generating heat pump is going to provide both heating and cooling at the same time. And as you can see, there are different layouts of the systems possible. So for example, in the right in the left side, you can see the simple distillation tower system, while on the right side, if there are other processes that the distillate has to go through that need steam, then the heat pump can produce steam also for example, this thin film evaporator. There are also, in this case, different heat pump concepts possible for steam generator. For example, there is heat pump and flash tank, in which the heat pump produces hot pressurized water that is then fed into a flash tank, where the pressure drops, causes the part of the water to evaporate, and then this steam is extracted from the tank and is then fed into the distillation tower. Otherwise, the heat pump can be combined with a mechanical vapor compressor, or we can also have an open loop with a mechanic vapor compressor. The third example is an example of hot water, or production, or just heating of a liquid working fluid. That is the case of processing of oil and gas. Processing of oil and gas requires different phases, and here we're going to show the separation that is an important and energy consuming part. So the separation of oil and gas requires different temperatures according to which fluid we are refining, and normally the temperature required is the process is the heating required is produced by the combustion of part of the gas produced. While integrating a heat pump, then there are different possibilities. So the condenser of the heat pump can directly serve as a heater for the process, and then since the oil and gas need to be cooled after the process, then the cooling is gonna act as heat source over the heat pump. And then this concept, so in this concept, then the heat pump is integrated at process level, then has its advantages, because the temperature lift is more limited, and therefore it needs fewer compression stages and more refrigerant choices. But it's of course a tailored integration that is more complicated to design. While the heat pump can also be integrated at on a supply level, so it's the heat pump is gonna supply heat for the central heating system with a dedicated heat transfer fluid that is usually hot oil on the heating side and the water glycol mixture on the cooling side. And this integration is requires higher supply temperatures, and it's easier. It's an easier integration in which you can use more standardized heat exchangers. But since the temperature lift is higher, then the heat pump design itself can be more complicated, because there might be need for the different refrigerants and a cascade system. So you can see here that there are different heat pump concepts possible. So single stage heat pump is suitable when the temperature lift is not too high, while when the temperature lift required is higher, then a cascade heat pump is necessary. Okay, so this was an overview of of 3 selected examples, and now Florian is gonna give the summary of all the concepts that we have analyzed.
Yeah, thank you, Virginia. Based on the collected integration concept examples, we have tried to derive kind of systematic that can be used to qualitatively match process requirements on the one side of the different processes with the characteristics of the different heat pump concepts we see on the right side here. And the visualization is to be understood as a qualitative orientation without any claim to completeness. Rather, it is intended to summarize the most important parameters according to which different heat pump concepts can be developed on. Yes, it provides an overview of process types here on the left side of the slide, and the influencing parameters for the characterization of the heat source and the heat sinks. And it also provides qualitative recommendation on the right sides for the single heat pump concepts from different heat pump applications, which in the end are suitable for fulfilling the process requirements described in the heat source and heat sink column. Yeah, the overview summarizes and categorizes the main thermal processes into the following basic operations. We have drying with different processes. We have hot water or thermal oil heating. And we have thermal separation, thermal preservation, and thermal treatment process category. For example, for the drying unit operation, as we have heard before, the warm, humid exhaust air is usually available from the drying process as a heat source for the heat pump to heat the drying air up to the drying target temperature. And depending on the target temperature lift, and also the temperature glide on the heat sink side, single stage heat pump concepts for smaller temperature lifts, or cascaded transcritical heat pump concepts for higher temperature lifts and higher temperature glides, as well as Stirling heat pump concepts for high target temperatures and high temperature lifts, or reverse Brayton cycle heat pump concepts for large temperature glides are suitable, for example, to fulfill the requirements of drying processes or in general for processes with media which have large temperature glides. And a similar logic applies to heating of hot water or thermal oil, which is the next category. And if on the other side, we have processes from thermal separation, preservation, and treatment, which can be supplied by steam generating heat pump concepts. And depending on the target temperature and whether vapor can be directly recompressed or other heat sources need to be used, the following heat pump concepts are available, which can be direct steam generating heat pumps, and if necessary, with additional downstream steam compressors, heat pumps using flash tank for steam generating, steam compression in combination with evaporator, or by mechanical vapor compression, or in the end, a combination of these concepts. And most of them we have already seen on the slides from Cordin in an application example. So I won't go into much more detail here. In addition, the scheme shows production patterns such as continuous or non-continuous operation, which influence the need of the thermal storage. And moreover, the integration concept can be also distinguished according to their integration level on process, unit, utility, or site level. Yeah, on this slide, you see an overview on the 12 integration concepts we have developed during task 2. And these include 6 drying processes, like the shown for spray drying, 3 thermal treatment processes with baking, anodizing, and extrusion cooking, and then the 2 shown thermal separation processes, and sterilization as the thermal preservation process. We have described all the integration concepts according to the corresponding unit operation, the production pattern, the in and outlet temperature of the heat source medium and the heat sink medium, the sink and source side temperature glide. Then we make some visualization of the corresponding temperature range. Then we have information about the mean temperature lift between heat source and heat sink, the integration level, then the potential heat pump concepts and the corresponding heat pump application. I won't go into much more detail here right now, but if you're interested, all integration and heat pump concepts can be found in the final report of task 2. Yeah, as it could be seen from the shown examples, the understanding of process requirements is really crucial for the proper integration of heat pumps. Pinch analysis, for example, offers graphical representation for the efficient integration of heat pumps. And yeah, in total, we have described 12 processes. We have derived 27 integration concepts for these processes, and we have suggested 15 heat pump concepts. Yeah, this brings me to the end of our talk, which leads me to refer again to the final report, where the multitude of integration and heat pump concepts can be viewed. And yeah, first of all, to thank again all other co-authors which has contributed with the integration concepts to this task. And yeah, thank you for your attention. And I think we are happy to answer your questions.
Thank you very much for the interesting presentation, Florian and Virginia. I think we're a bit behind schedule, but maybe just one very overall question. You had a look on all these integration concepts, but also the heat pump concepts, and you had this very comprehensive chart on how to match these. But could you give maybe the main conclusions? What's most important to take into consideration when selecting the technologies for a given application?
So from my point of view, is to understand the actual requirement of the process. So we have to think about what is the inlet and outlet temperature requirement, what is the requirement regarding heat exchange, and where we don't have to look on the existing energy supply system, because we were not able to put the heat pump in the energy central. We have to put the heat pump directly into the process to be more efficient. So what I want to say is that we have to match the process requirements in terms of the temperature load profile with the heat dissipation profile of the heat pumps to have a really efficient integration in order to have high COPs and have high economic feasible integration concepts.
Perfect. Thank you very much for answering these questions. And I believe there are some other questions in the Q&A. So let's keep it here. Thank you once more. I have announced a break, so I would suggest that we have a short break. On my time, it's now 17 minutes past, and I would suggest that we meet again in like 3 to 4 minutes, so 20 minutes past, and then we'll continue with the presentation about the task 3. So see you all in 3 to 4 minutes. Yes, welcome back, everybody. I can see that Sabrina says the break is over, so seems like we can continue, and I think we can slowly get started here with the task 3. Task 3 was again about if we now have these nice concepts which show very well integrated systems, how can we actually move towards these kind of concepts when we look at real sites? And here a guideline has been developed, and Sabrina Dusek from AIT will present the developed guideline. So please, Sabrina.
Hello, I hope you can hear me. Hello also from my side. As already said, my name is Sabrina Dusek from AIT, Austrian Institute of Technology. And on the behalf of the Task 3 working group, I will give now an overview of the main results from Task 3. So I will give a very short introduction why we done this in this task, because decarbonization has already a high priority for industry, especially the decarbonization of the process heat supply. The path to complete decarbonization is often not totally clear, and the strategies differ for one industrial company is different for another. So company-specific strategies are needed to get a good strategy. You need a holistic approach to look at the total site to minimize problems, and such strategies influenced by many factors, external conditions, also company goals. And for the development process of such a strategy, you need a lot of knowledge. So you need to know what the process is, you need to know technologies available, and also technologies which will be in the future available. So as we know, high temperature heat pumps are a key technology for decarbonizing process heat supply. And so in the course of the task 3, we dealt with the strategy development process to improve the implementation of such technologies as high temperature heat pumps, which are an efficiency increasing and also electrification measures. We have the information collected and summarized in the task 3 report. We also, as Benjamin already said, developed a guideline. It's more or less a compact version focusing on graphics. Yes, and this is also on the task 3 homepage. You can see here the link on this slide. So what's the document about, or what we wanted to what is the objective of the guideline rules of the task report is to support companies in the development process of decarbonization strategies. So the main topic is goal setting, analyzing current status, developing concepts, and driving their strategy. So we, as already said, or also the title of the presentation said, that we're focusing on decarbonizing of process heat supply. So the first main topic is goal setting. So how to define a decarbonization goal. At the beginning of such a strategy development process, you need to think what is important for you. The start is the definition of the overarching goal that must be defined, and also the time frame in which this goal should be achieved. Goal setting is influenced by many drivers, as you can see in the picture on the right: legal requirements, for example, or financial advantages. It is important to elaborate the importance of the different drivers and to clarify the ambition level, because it influences the timeline. And you need to define how important a goal is compared to another company goal. It is important to clear and well communicate these goals. Another very important part of the strategy development process and for the step of concept solution development is the data collection. So the description of the current status and also the reference scenario. which is used to evaluate concept solutions. So which information is needed? In the picture, you can see some example for information which is needed. You need to define your process cooling demand, your process heating demand, also the waste heat available. You need different parameters which defines this demand, for example, temperature, mass flow, media, and so on. It is also important to have this information for a characteristic time period, so to consider time-related changes, for example, in the availability of the waste heat, to get a good solution. It is also important to consider interconnections between different processes and other boundary conditions. What is also needed to collect an information is what is needed in the future. So also to have a little bit in the future, what will be the production capacity, and is there any equipment which will reach its end of lifetime? This should also be considered. And it is important, as already Florian said before, it is important to know what the process needs and not only what's the actual supply system delivers. When you have here a good database, you can start with developing the concept solutions. So first of all, you need to know what technologies are available for decarbonizing the process heat demand. Here on this slide, you can see some examples divided in 4 categories: efficiency increase, electrification, renewable gases, and biomass. The heat pump is mentioned in the efficiency increase category and also in the electrification category, as it fits in both categories, especially when electrical driven heat pumps are used. The concept development process is not easy. You have very case specific, application specific concept solutions, or they need to be developed application specific. There are different methods available, for example, pinch analysis, physical modeling, mathematical optimization, which can be used to develop concept solutions. It needs to also, the site-specific parameters need to be considered when developing such concepts, for example, connection power, space availability, and so on. And as presented before, the integration concepts collected in task 2 maybe can be the basis for such concept solution development. Especially focusing on heat pumps, and one important topic is also to need to know what is the level of integration for the heat pump, or to think about what's the most suitable level. You can see in the picture on the right 4 different levels: process level, unit level, utility level, sector level. So as the picture show, sector level is, for example, a heat pump which uses district heating as heat source and provides process heat to an end user. And integration on process level is very near to the process. For example, as using the process media after the process, compress it and feed it back into the process. The heat pump integration is, or this measure is the generally most efficient on the process level, but on the same side, the process modification required is also maybe the highest on this level. On contrary, the flexibility is highest on sector level. To find the best integration level depends on the current system layout, available heat sources and the location, and also the location of the sinks, and on the planning horizon. When there are concept solutions developed, you need to compare them and evaluate them. So will it pay off is the question which should be answered. In the picture on the left, you can see some examples for key performance indicators. They can be the economic and also non-economic evaluation criteria, and you need to define the most important and also how important is one KPI compared to another. In the right picture, you can see an example for comparing different, let's say, concept solutions are based on a levelized cost of heat as a function of the price ratio of electricity versus natural gas price. It's only an example how it could look like. When the concept solutions are selected, you need to start, or it's good to start defining an implementation roadmap. So there are different influencing factors which should be considered in the roadmap. For example, technology readiness level of a technology, delivery times, influence on the production, and so on. As we said, based on the concept solution, sub-projects can be defined, and also the timeline. It needs to be defined. The team, is the know-how needed internally available, or do I need external know-how? And to get the roadmap, it's also good to define milestones and targets. To minimizing the risk, it's good to test critical solutions or technologies with a lower TL first on a smaller scale, and then implement them later in a full scale. It's also good to include redundancies. Ongoing resource assessment of the current status and targets should be considered, and also backup strategies. So we gave an example a theoretical example how a roadmap maybe could look like. The starting point was an fictive industry company which has a hot water demand and also a steam demand. And here you can see the timeline of when measures should be implemented. It's, as I said, it's a theoretical example. So we started with the measures for reducing the heat losses should be implemented. Then the measures for direct heat recovery as heat exchangers. Then also, as we need electricity for the heat pumps, the requirements established for electrification. Then first steam generating heat pump is integrated. In the next step, the heat pumps for hot water production are implemented. And afterwards, the more steam generating heat pumps are implemented. And then the last step is the electrification of the remaining heat process heat, and to get a 100% decarbonized system. So I'm almost at the end of my presentation. So the conclusion is that developing a decarbonization strategy is a complex process and it needs time. Many factors must be considered during this process. Clear goals and a database are really needed to get a good strategy. The concept development is also very site-specific and process-specific, and the evaluation criteria must be clearly defined. Target is a clear and implementable decarbonization roadmap. So in the end, so thank you for your attention.
Thank you very much, Sabrina. Very good presentation and a nice overview here. One short question from my side. I mean, you explained it that it's a good idea to be very strategic here and to have a long-term strategy on how to convert. But can you elaborate a bit more? What are the main risks of not having such a strategy? I mean, the companies are having energy efficiency programs and so on. Why is it not just business as usual, and why will their standard ways of doing or implementing energy efficiency fail in this case? So
yes, it is so that you need to have a total view on the side, and also a long-term view to have to implement a measure so that the implemented measure influences each other in a good way, so that they can support each other. So to have don't implement a measure which maybe hinder another, which will be implemented later on, maybe in terms of efficiency. And so that's why it's important to have a plan. Yeah.
Mm-hmm. Perfect. Thank you very much. And once more for the presentation, but also for coordinating this task. To anticipate the questions, also this report and the guideline are available on the homepage. So make sure to pass by. It's always a very complex presentation, but there you can have a look at both documents again. And we will move on here to task 4. Task 4 was on how to define and test specifications of industrial high temperature heat pumps. And here I would like to give the floor to my colleague Emil, and together with Fridolin Møllerholm from Vigard Mobile.
Thank you very much. I will just share my presentation. There we go. Okay. Yes, my name is Emil Petersen, and I'm from the Danish Technological Institute. And I'll be presenting the Task 4, Annex 58 Task 4 report, titled Definition and Testing of Heat Pump Specifications. So first of all, in this task, in short, is meant to be a reference work. So if you are involved in a high temperature heat pump project, this is meant to serve as a help to you. So it aims to answer the 3 major questions on the slide right now. So what should be agreed upon by all parties during the project? How does the supplier promise the performance of the heat pump in a transparent way? And how is the heat pump performance tested and verified? Yes, and the Task 4 report is available on the Annex 58 homepage for using the link here. Yes, so in a industrial heat pump project, as the end user, you will need to specify to the supplier some criteria of for this heat pump. What is it supposed to do? What sort of conditions should it perform in? And in order to best have the best conditions for the supplier, in this Task 4 report, we have given some recommendations for how to some of the things to focus on when creating such a tender. Yeah, some of the most important things are that you must specify your boundary conditions of the heat pump, so your sink temperature and your source temperature, the medium flow rates, as clearly as possible. And also the variations of these, what can be expected. You should not limit your tender to specific system designs. It's best to give the supplier freedom to design the most optimal system. And then we also recommend using evaluation criteria in your tender, so you could let your supplier know which factors do you find most important. So that could be CapEx, OpEx, the COP of the system, general Q&A, quality of the system, etc. And these could be weighted as shown on the figure on the right, to signify to the supplier where they should put the focus. And lastly, penalties and bonuses related to, for example, the performance of the heat pump could also be a tool to ensure that the heat pump will perform as promised. Yes. Then the report also goes into 3 guidelines. So the first is the specification guideline, which serves to help with specifying all the important things to remember in a heat pump project. Yes, and the second guideline is a laboratory testing guideline on how a factory or laboratory test should be performed. And then lastly, the on-site testing guideline, which is for how a site acceptance test is performed for a large industrial heat pump. So firstly, the guideline for specification of heat pump projects. Again, this tries to answer what information should the end user and the supplier have agreement on. The guideline mainly consists of details on what to specify regarding boundary conditions, the design of the heat pump, and performance of the heat pump. It also lists a number of things to have agreement on regarding equipment. Do you have material requirements? Does it need to be stainless, for example? Do you need the intermediate loop on your heat exchanger because you're worried about leaks of refrigerant or oil, for example? Safety and environmental requirements. Are there any tests that testing standards that you've as an end user feel must be performed so that you know that the heat pump lives up to whatever standard that you require? Yeah, etc. In this guideline, we also present a method for the supplier to promise the performance of the heat pump in a transparent way. And you could, as the supplier, calculate your expected performance for a set single design point. So for a given source temperature and a given sink temperature and a given flow rate on each side, you promise a certain performance. But you will find in reality that once the heat pump is installed, that it's very unlikely to hit exactly these design conditions. And especially over time, you will most likely have varying conditions for the heat pump. So in this figure, on the x-axis of each of these 4 graphs, you see the source inlet temperature, and on the y-axis, the sink outlet temperature. And each graph signify a different temperature glide on the sink and source respectively. And this is an example of how such a performance map could be made. So here you have many different operating conditions shown, and you could for example plot okay, we have a source inlet temperature of 80 degrees and sink outlet temperature of 140, and then you end up here for these temperature glides, and then you know exactly this is the promised performance. Yes, the next guideline is the guideline for laboratory testing. And this is, of course, a test of the heat pump in controlled conditions. And here we recommend a full load test and a partial load test. And for both of these, it's important, as shown in the performance maps, that you test the entire range of the operating conditions, so you really know the performance of the heat pump in all conditions. Then we also recommend a ramping test where you measure the startup and shutdown time, as the energy spent during ramp up and shutdown is mostly wasted energy and is important for calculating, for example, seasonal COP or the OPEX of the system. And then we also recommend standby and off mode tests, which are intended to measure the electrical power consumption when the heat pump is not operating. And such a test result could be shown as in the table here below, where you have different temperature lifts of the heat pump. and the resulting COP and heating capacities, and also the standby losses. This graph is just a quick view of, so this is based on entries from the Annex 58 participants, all the research technology organizations that have participated in Annex 58, and their testing facilities. So we see that there are a number of testing facilities out there, and these are globally RTOs from all over the world. And we have a number of testing facilities in the megawatt range, as can be seen. But of course, there's a limit. So we don't see anything above 2 megawatts, as this is probably just too impractical. Which brings us to a guideline for on-site testing, because in the case of large industrial heat pumps, it's in many cases probably uneconomical to perform a factory acceptance test. And then you will have to sort of make do with the conditions that you can get on site. And we have this process as shown here in the slide. So for this on-site testing, you need to start with having some performance promised ahead of time for a given operating range. You will then operate your heat pump on your site, and then define what the steady state look like in that process. And I have a graph here. So, for example, you might have a sink temperature that varies up and down like this, and a source temperature like this. And you can see it's never fully flatlined. It's never completely steady state, but you might accept these variations as within some margin, and this is your definition of steady state. So you might say plus minus 1 Kelvin on the source and sink inlet. Then you perform your measurements while you have this steady state condition, and then from that you can compare your results with the promised performance. The report also contains recommended sensor measurement uncertainties. So what precision should your sensors have? And these are based on industry standards related to heat pump testing. And it also includes calculations of what these uncertainties mean for the resulting COP. So if you have a given sensor uncertainty, how will that affect the uncertainty of your calculation of the COP and also the heating output of the heat pump? So you could calculate backwards from that and find what sensor accuracy do you want if you need a certain uncertainty of your COP. Lastly, you might have that your on-site conditions look more like this. So it's really hard to define steady state. And one way to get around this would be to use a simulation-based approach. So you could build a model that you validate for your on-site conditions. So you fit your model to your measurements, and you can replicate these measurements with your model. And then you can use this validated model and run it at design conditions and compare these results with the performance that is promised in your contract with your supplier. Yeah, and then of course, such a simulation model is very valuable and could be used for optimizing the system as well. And that was it for my presentation. So I'll stop sharing. And now I will give the word over to Fridolin.
Hello, everyone. I will just see if I'm sharing the right one. Do you see my presentation?
Yes, we see
it. All right.
Oh, we see your presentation mode.
Okay.
Just so you know.
Actually, I do not know how to shift from that. Anyway, I think I'll just run the presentation like this. We only have a few minutes left. So what I will highlight or present from the task 4 is some cases and some examples that I will highlight some different issues related to the tests that we have seen for different cases. These are also described in the report. The first case, what I would like to highlight here is an example of the extension of the test, and also the testing period. This was a heat pump for utilizing surplus heat from a process. Both a FAT and a SAT test were planned, and a lot of parameters were sort of decided to be parameters that should be studied and be within certain limits according to the contract, and these should be both evaluated during the FAT and the SAT test. And the challenge was that the SAT tests were done on a independent institute and with a limited amount of time, of course, due to limited amount of resources. And of course, every time we ask for something in a test, this comes with a cost. And I think this is also a very important thing to keep in mind when we ask for something. Then this will often come as a cost. And what we have learned from this test is also, I mean, was this test overkill? Should we actually test for all these different parameters? So be more critical of what we actually ask for when we are writing the specification of what we want to have tested. To what extent should we actually test a technology that is mature, or if we reckon that the technology is less mature, should we have more specific tests? So these are some of the questions anyway that we have evaluated afterwards. Should we have is this the same test that we want to run both on a SAT test or on a FAT test, or should we, to a greater extent, differentiate between these two tests? How do we deal with long-term testing? And this is a case where we've actually had a challenge with the heat pump afterwards, because after a certain amount of hours of operation, then we were facing some challenge with the heat pump. And this was not something that we could discover on a FAT test or SAT test. So the money spent or the effort spent on doing these tests did actually not cause the challenges that we were facing afterwards. And of course, then we could also consider adding some penalties that could actually maybe substitute some of the prices for the FAT and SAT test. So putting more penalties onto the supplier, but of course that will increase the risk from the supplier, and then again come with an additional cost. So these are some of the pros and cons that we have in terms of this project been facing. This is another example of a data center cooling system where we had a problem with the integration. The FAT tests were done and from the supplier at the supplier's facility, and it were found okay. But during the SAT tests, we discovered that we should that there was some design issues that were not taken into account during the initial design of the system, and this was a design problem during a startup. And the way that we dealt with this was that it was actually covered by the warranty. So some money were held back in order to actually cover any issues. But I mean, this was a problem that was very hard to foresee initially in the initial design phase. So, and it was not a problem that could be detected during the FAT test. So luckily we had this warranty that could actually cover this this issue. The other example here is a problem where process cooling were made for district heating. And the sort of the conflict was that that an issue occurred by fouling of the heat exchanger, because we were actually using a cooling tower where we have some dirty water present, and even though a filtration system were integrated, this still caused problems due to fouling, and that actually affected the coefficient of the performance. So now we had a discussion with the supplier whether we should, it was a fouling issue that actually was the main problem, and how this will affect negatively on the performance of the heat pump. And that actually also challenged the test conditions, because we have the fouling to take into account. So yeah, there was another sort of issue that we have been dealing with. Luckily, this was something that in the contract was sort of handled, so it was something that the supplier should deal with. But this is just to stretch that sometimes there can be some more indirect issues related to these performance tests that is not very very clear. Benjamin, I don't know, we have 2 minutes left, and I have one case left. Should we skip that, or?
Yeah, maybe we it's a good idea to skip that, because then we conclude here.
Yeah.
So thank you very much for the presentation. I think it was a very great contribution here, both to the presentation and to the annex. I think it's very important to have these practical aspects taken into consideration. The high temperature heat pumps, they are often more complex. They might deliver heat at several temperature levels. They are dealing with process streams, you mentioned it, fouling, and so on. So it's often highly integrated. And I believe it's very important here to leverage these experience, which we already have from industrial heat pumps, and make sure that we don't do the mistakes again for high temperature heat pumps, and that it would be a real support here. So thank you very much for that contribution. I have just 2 very brief slides on to conclude with. So we have seen about the Annex 58, where we came from, all the work we did, and this is quite comprehensive. As we said, we had 14 countries working over 3 years, so there's quite many materials available, and all this can be found on the homepage. You have also seen it here, but you also might wonder, okay, what's actually next? So what's coming after this annex, and after all these reports have been done? Just one point, there will be a lot of more heat pumps being implemented. We had these numbers from the IEA saying for light industries, only light industries, we would need 500 megawatts per month being installed to decarbonize heating, process heating most optimally. I put these numbers, some time frame into this perspective, and this means half of the potential should be realized by 2030. 500 megawatts per month, that's huge, maybe even more than we can realize. And showing at this curve where we see we didn't implement so much now, then it would mean that we would have even more during the coming years. So it's very exciting times ahead. And still the same point goes, communication is key to exploit these potentials. We're concluding this Annex 58, but we're also preparing a follow-up activity, also related to high temperature heat pumps. We are currently working on the idea generation. This will include activities such as maintaining and updating the technology overview, the demonstration cases. We might also proceed with the guidelines for developing integrated concepts here. We also discussed to produce some education materials, because it's very important to have many people along the entire value chain to understand the potentials here. So all this will be formulated as a draft legal text. We will then submit this draft legal text to for comments, and at some point approval by the ExCo. Then we will at some point have a final legal text. We will build the consortium here. This is already in parallel happening now. And then we hope finally to start this annex, the follow-up annex, early 25, most probably during the course of 3 years. You're welcome to announce your interest to me by mail. You have my email address here, and just reach out to by mail or LinkedIn or whatever, so then we can keep you included in further communication for this. And with that, I would like to thank you all for attending, for following over this time. I would like to thank all presenters for sharing the presentations and knowledge here today. And I would like to say a huge thank you to the entire project group. It has been very exciting years. I put a picture here from the time when we met in Aarhus, visited a heat pump. I very much enjoyed the time. I think it was very productive. It was you making this annex what it became. I think it was very valuable, well received by industries. And yeah, once more, a big thank you to all contributors. And lastly, also a big thank you for all you attendees here today. So thanks once more, and yeah, let's keep in touch. So thank you very much, and goodbye.